Добрый день.
Good morning, distinguished colleagues, dear guests. So may I declare the meeting of the Dissertation Board on the dissertation by Nadezhda Podrezova in compliance with the requirements for the candidate of Maths and Physical Sciences under the title Simulation of the Sea-Dense Water Flows with the Count of Bottom Pumping in the subject 250028 Oceanology to declare open. According to the resolution of St. Petersburg State University as of April 26, 2017, number 4252/1, me, Mr. Zakharchuk, Doctor of Geographical Sciences, Professor, Oceanology Department, St. Petersburg State University, is appointed as chairman of this dissertation board. The members of the dissertation board are Tatiana Belonenko, Doctor of Geographical Sciences, Professor, Oceanology Department, St. Petersburg State University, Valentin Roshkov, Doctor of Physics and Math Sciences, Professor, Department of Oceanology, St. Petersburg State University, Vladimir Ivanov, Doctor of Physics and Maths, Senior Research Fellow, Arctic and Antarctic Research Center, Roshydromet. And online, we have a connection with Alexei Androsov, Doctor of Physics and Maths Sciences, Research Fellow of Polar and Sea Research Center by Alfred Wegener, Germany. According to the federal law as of August 23, 1996, number 127, St. Petersburg State University has been granted an exceptional title to award academic degrees. A relevant decree under this meeting was issued on September 1, 2016, 6228/1. Under this decree, the meeting of a dissertation board is legitimate unless if no less than 2/3 of the initial composition are present. So we have the quorum here because all the 5 members of the dissertation board are here, including Mr. Androsov, who is online with us, and we have an audio and visual contact with Mr. Androsov. So the quorum is here. So may I stipulate the following agenda and the time frame for this meeting. The overall time frame should not extend 2 hours. First comes a short report of the chair on the documents presented by the defendant, their compliance with the requirements, and replies to some potential questions, 5 minutes. A short report of the defendant, echoing the key findings of the paper, 20 minutes. Third, questions to the defendant, 2 minutes maximum per question. A review of all the reports submitted by members of the dissertation board. All the reports were downloaded to St. Petersburg State University website. Therefore, please focus on critical points only. Next, reply to members of the dissertation board and external reports. 15 minutes maximum. 6, open discussion and statements by members of the audience who are not members of the dissertation board. Only strictly relevant suggestions, questions, and feedback addressed to the defendant are accepted. 5 minutes per each speaker. All willing to take the floor should register in the registration list beforehand, and please introduce yourself before delivering your statement. 7, defendants reply to statements of the audience who are not members of the dissertation board, 5 minutes maximum. 8, statement of the research supervisor, 3 minutes maximum. 5 minutes break before open voting on rewarding the defendant with the expired academic degree, pass or fail. So the discussion between members of the dissertation board is not broadcast online. 10. Open voting by name count of vote and registration of the voting results in the protocol. Pass or fail. 11. Concluding statement. The decision on whether the defendant has passed or failed. And lastly, number 12, a concluding statement by the defendant. Well, before I proceed to implementing the agenda, may I urge everyone to switch off their mobile devices. Thank you very much for compliance. May I also inform you that we have audio and video recording broadcast live on St. Petersburg State University website. Simultaneous interpretation from Russian into English is also provided. Any questions on the agenda? So may I then enjoy my title of a chairman and proceed to the first point of the agenda, a brief report of the chair. The dissertation submitted by Nadezhda Podrezova in compliance with the requirements for the candidate of physics and maths in 250028 Oceanology under the title Simulation of Sea-Dense Water Flows with the count of bottom pumping has been submitted and accepted for defense on April 28, 2017, under the resolution 4354/1. The composition of the dissertation board was approved on April 26, 2017. Resolution number 4252/1. The composition of the dissertation board has already been stipulated. The following documents were submitted by the defendant. Application addressed to Rector Kropachev on acceptance of the dissertation for defense submitted in March 2017. Second, copies of the degree. Third, certificate proving the successful results in the postgraduate exams. The review of the research supervisor, Professor Tsaryov, St. Petersburg State University. Recommendation for defense, signed by Rector Mikheyev. The list of publications, including 7 papers reflecting the key findings, including papers published in reviewed journals, included in the Higher Attestation Commission list. And lastly, the dissertation in Russian and in English in soft and hard copies as a manuscript. I should note that all the documents are in compliance with provision 12, section 3 on the academic degree awarding procedure in St. Petersburg State University, appendix 1 to the decree. All the documents are thus submitted according to the agenda. Our next point is a brief report of the defendant on the findings of the paper, 20 minutes maximum. Please, the floor is yours, Nadezhda.
Dear ladies and gentlemen, dear members of the esteemed council, I'd like to draw your attention to my paper on the topic simulation of near bottom density flows in the sea, taking into account of bottom pumping. In the 60s of the last century, was shown that with the divergence or convergence of the benthic Ekman currents, vertical currents formed on the upper boundary of the bottom Ekman layer. This process is called bottom pumping. The bottom pumping formed during the distribution of the near bottom density flux with a noticeable effect on its various characteristics. Up to now, with respect to the formation of pumping in and the near bottom density flow, so its effect on the near bottom density flux has not been practically investigated. Pumping is the process of forming vertical currents caused by the divergence of near bottom Ekman flows. Benthic density flows in the seas play an important role in the formation of bottom and deep waters, background distributions of temperature and salinity of water, as well as background horizontal circulation and vertical currents. In most existing models of the distribution of near bottom density flows in the sea, there is no adequate consideration of the influence of bottom pumping, as a result of which the role of this factor is in the formation of near bottom density flows in the seas remains insufficiently studied. Research objective. The main purpose of the study is to study the regularities of the manifestation of pumping in the formation of bottom density fluxes. Research objectives. Estimation of the contribution of hydrostaticity in the dynamics of near bottom density flows, formulation of a mathematical model of near bottom density flows taking into account the influence of bottom pumping, research using the modeling of the structure of vertical currents arising under the influence of bottom pumping. Provisions to be defended. Model of near bottom density flows in the sea taking into account the influence of bottom pumping. Features of formation and distribution in the basin of near bottom density flows taking into account the influence of bottom structuring and third, features of the distribution of bottom density fluxes in the wide sea taking into account the influence of bottom pumping. The structuring of the bottom pumping into the near bottom density flow is presented on the slide. Baroclinic vertical currents are formed under the influence of bottom pumping. These contracts affect the sea surface. As a result of the adaptation process, interconnected barotropic horizontal flow velocities are formed. Barotropic vertical currents arise at the bottom due to barotropic pumping. The influence of vertical currents can be represented both directly and indirectly. Direct is direct due to advection, and which leads to a change in the shape of density flows. Model of the model of near bottom density flows. When the model was formulated, a comparison was made of the horizontal pressure gradients for the bottom density lengths obtained with the help of not hydrostic and hydrostic model. It was shown that for the characteristic slopes of the seabed, the difference between them is insignificant. Taking into account the obtained conclusion about the admissibility of using the hydrostic approximation, the hydrostatic equations of motion were used to describe the flow velocities. The calculation area was divided into two regions. One was located at the bottom and had a thickness of 20 meters. The second was located above the bottom to sea level. Equations of motion continued to salt transfer were recorded for the selected regions using S coordinates. To calculate the vertical near bottom currents formed due to bottom pumping, the equations presented on the slide was obtained. The equation includes a number of terms characterizing different mechanisms of formation of bottom vertical currents, which are illustrated in the figures. The first term of the equation associated with the divergence and convergence of the bottom Ekman flows on the right and left boundaries, density flux, respectively. The second term of the equation associated with the effect of heterogeneity of the horizontal distribution of density and thickness within the flow. The third is the divergence of the Ekman currents associated with a change in the slope of the bottom. Fourth is with the influence of the disturbance of the level of the sea surface. It was assumed that the velocities of vertical currents calculated from the equation form a perturbation of the level of the sea surface leading to a barotropic adaptation process. With the help of the developed model, the features of the propagation of density flow in the basin in the form of the symmetrical funnel are investigated. The depth of the center of the funnel is 300 meters. The dimensions of the calculated area are 160 by 160 kilometers. The step is 2 kilometers. The number of computed nodes is 80 by 80. The figure shows a source with a constant salinity of 30. The surrounding water has a salinity of 29. The figure also shows that the two sections on which the resulting sections were built. The slide shows the distribution of bottom density flow without taking into account pumping by calculation under the influence of the presence near the bottom of the region. The surrounding water has on the section were built. Figure D shows the distributions of the velocities of the flows of the bottom density flow at a distance of 1 meter from the bottom of 20 days. Features of the formation of vertical velocities of currents. A. Vertical currents that form along the edges of the density flow due to the divergence of the near-bottom Ekman currents. In the vicinity of the left boundary, a region of negative directed upward is formed along the direction of the flow. And in the vicinity of the right boundary, a region of positive vertical velocities. B is the distribution of the components of the near-bottom vertical velocities at the upper boundary of the Ekman layer. In the central part of the stream, a region with a positive vertical velocity was localized, and at the lateral boundaries of the stream, regions with negative vertical velocities were located. In the central part, the divergence of the Ekman currents is formed along the width of the stream, and accordingly, the descending vertical velocities. On the sides, upward negative vertical velocities of currents are formed. C. With the descent of the flow, the center of the region, there is an increase in the convergence of the Ekman flows due to an extreme increase in the curvature of the flow trajectory. The maximum values are reached at the point corresponding to the center of the basin. As a result, a sharp increase in the thickness of the bottom flow is noted in the center of the region. All speeds are negative. Distribution of salinity calculated on the basis of various factors. A. Without regard to vertical velocities. B. Allowance for vertical velocities at the lateral boundaries of the density flux, taking into account the vertical velocity, the shape of the transverse flow profile changes. There's the decrease in the thickness of the bottom edge, the bottom layer of the slope of the bottom, and its growth at the near edge of the density flux. And C. The total effect of the second opponent is manifested in smoothing the inhomogeneities in the cross-section of the density flow, as well as in reducing its thickness. And the next is the formation of a bottom density flow with all velocity components of vertical currents taken into account. The homogeneity in the distribution of salinity in the center of the region has become much more smooth. It has a smaller vertical dimension and is distributed throughout the entire area occupied by this stream. Next, we turn to the study of indirect effect of vertical velocities, the bottom density flux. The results of the calculation show region with positive and negative velocities of vertical currents. Thus, in the vicinity of the center of the region, a region with ascending regions is formed, and around it there is a region of descending currents. And the barotropic vertical velocities, the main feature of the vertical currents related to the density flow, was localized in the center of the region of ascending vertical currents. Further, a study was made of the manifestation of barotropic vertical currents on the dynamics of the bottom density flux. Calculations show that with the passage of time, the total vertical currents are weakening, and apparently taking barotropic vertical currents into account reduce the thickness of the near bottom density flow. When barotropic and baroclinic currents are added, we can observe a two-layer structure of flows. The bottom density flux moves against the clock of the arrow background. Water has the opposite sign of currents. Water moves clockwise. In order to take into account the influence of barotropic horizontal currents arising under the influence of pumping, they were included in the calculation schemes. The inundation of the Barents Sea water in the central deep water part of the White Sea plays an important role in the formation of various hydrological characteristics, including the renewal of bottom, the distribution of salinity and currents. Further, the possibility of reproducing a model for flooding the Barents Sea waters into the basin of water of the White Sea was investigated. The calculation area includes the Dvinska, Kandalaksha Gulfs and the White Sea basin with the size of 135 to 53 knots horizontally with a step of 3 kilometers. Vertically, the grid is 14 knots. The initial salinity distribution is assumed to be homogeneous and equal to 29. At the boundary with the throat straight, a salinity of 30 is set in the bottom layer of 30 meters thick. Under the influence of a great density of water and the slope of the bottom, more saline water from the throat is thrown into the central part of the White Sea. Further extends predominantly along the isobaths. The width and velocity of the flow depends on the inclination at the bottom and the salinity of the propagating water. The bottom salt water is distributed in the form of relative narrow bottom flow towards the Kandalaksha Gulf. The total vertical baroclinic flows at the center have negative velocities. On the other hand, positive ones. Baroclinic currents cause a disturbance of sea level, with the maximum height over the basin and the gradual regress to the periphery. The horizontal surface currents caused by the sea level disturbance have a clockwise direction. Barotropic vertical currents have the opposite direction of baroclinic. In the section of the distribution, we can observe the source of the right side as well as the left part of the stream which rounded the hollow. Based on the results of a study of the features of the pressure perturbation formation in the vicinity of a density lens, the feasibility of using the hydrostatic approximation in describing the horizontal flow velocities in the region of the bottom density flux, a mathematical model in the near bottom density flow was formulated. The feature of this is an equation for the components of the vertical velocities and currents due to the divergence of the near bottom Ekman currents, a block for calculating the barotropic adaptation process caused by the bottom density flux allowance for the interaction between the near bottom density flow and barotropic adaptation process, and also features of formation and distribution of bottom density fluxes on the example of a symmetrical hollow. What's the new things are proposed? The conclusions about the features of the formation of pressure perturbations in the vicinity of the near bottom density lens, the feasibility of using hydrostatic approximation in describing the dynamics of the near bottom density flow, bottom dense flow model taking into account the influence of bottom pumping, and conclusions about the features of the formation of density flow in a symmetrical basin. Thank you very much.
Questions to the defendant? Yes, please. Nadezhda, could you please roll your presentation back to the initial part where you show the results? This was the question by Professor Ivanov. So therefore my question. To the right. So this is the salinity distribution and then the velocities, and there is some area, right? And what's there? Just extremes, extreme values or what? So you see some symmetry there. Well, how should I approach? How should I reply from? Should I reply from here? I'll rather use the pointer. Okay, no, that won't work. Do you see that? But I don't see. So this is the initial part. Here the salinity is 30 promille. To the left, this is the flow that has that goes around the basin. Here you see the dissection, right? Well, okay, now that's more or less clear, but you did not make that clear in your speech. And here you see this tail. This is actually the second flow. Okay, thank you. More questions? I have a question. Do you hear me? Do you hear me? Yes, we do. Well, I have a question related to this graph. Here you see this point, the point of the open border. And the velocity gradient there is high. What's the explanation behind? There's a huge velocity gradient on the open border. The velocity gradient. Just the vortex structure. And what's the explanation behind the vortex structure and the high velocity gradient? Yes, this is illustration 13. I didn't hear you. Slide 13, please. This slide? Well, I don't see it from here, but I would like to see the velocity field. On the upper limit, you have this open border, where there is the outflow, and there is the vortex, a specific vortex structure. I didn't get that. You mean this slide? No, slide 13. And the illustration G, illustration number 4. What you have there is that anti-cycle structure of the general flow, and the upper border has a cyclone, the vortex structure as well, near the open border. What's the implication behind? How do you explain that? Well, as for this slide, we have this free surface disturbance, and this disturbance causes thermotrope velocities that have a specific vector, 10 meters per second. Well, so those are thermotrope velocities, right? Horizontal velocities. Why do they have a different vector? Different from the basic flow. So those diverge from the basic flow, according to your illustration. Why? Why do we see this vortex at the open border? Why do we see a vortex structure at the open border? This is the question of Professor Androsov. Well, according to this slide, as I understand it, here the process, this is just the adaptation process is on. Therefore, this the surface turbulence causes the horizontal flow that causes thermotrope vertical flows. Okay, I got it. Okay, clear. More questions, please? Mr. Roshkov, please. Oh, well, simulation. How did you do that? What was the protocol? Well, we just did laboratory simulation so as to prove that it was not the data, the direct data, but it's there is also some theoretical foundation behind that. No, we did not do any simulation in this respect, in what you mean. Well, it is all calibrated. You mean the equations? The ones you used? Well, in laboratory simulation, well, I read an article, a paper by Mr. Zatsepin, and he had a similar funnel, and the density structure changed along with isobars. And he had a similar structure as well. Professor Belonenko, Nadezhda, do you think that the validation of your model for the White Sea is adequate? If it is adequate, then why? Yes, I do believe that it is adequate because many simulation models do not include pumping. If we look at the White Sea, there's no explanation as to why the anti-cyclone vortex is there, whereas our model allows for some explanation. Nadezhda, I have a following question. It's well known, it's common knowledge that the White Sea is just an inflow sea. It's a tidal sea. So tidal forces contribute to the ocean, to the dynamics of the sea. So moreover, the sea is generated by waves that influence the mixing processes. And therefore my question, in your opinion, the density dynamics versus the tidal dynamics, how does those go together? Does density influence the tidal forces or not? Yes, I do understand that it is a tidal sea and tides are huge, make a huge impact. However, it is not well, has not well been assessed. But there is just little data on how density varies, and no simulation protocols have been implemented in this respect to understand this process, especially in regions of pumping. Are there any other questions? Professor Belonenko, yes, please. At the beginning of your report, you said that hydrodynamic models do not take into account the bottom pumping. Therefore, my question, can we somehow extrapolate your results onto those models so as to boost their adequacy? And if yes, then how? Well, I think we can try, actually. It's worth making a go at that.
Да. То есть это будем дальше пробовать.
Well, go on. Investigating that. We will be looking at that. Thank you very much. Any more questions? No questions. Thank you very much, Nadezhda. Please take your seat. So we are moving on to the report submitted by members of the Dissertation Board.
Сначала я зачитаю отзывы внешних.
I first start with the external reports. The report signed by a deputy head of the industry laboratory, Mr. Trofimov, and senior fellow of the industrial oceanology, Mr. Sintabrev. The report is positive, is in favor, and it has the following critical remarks. The introduction has a duplication of the results, and the wording is different in both abstracts. The second point of criticism is that in the introduction you mention the waters of the North Sea, whereas what is meant is the waters of the Barents Sea. And lastly, the conclusion does not include the objective of investigating the mechanisms of non-hydrostatic manifestation in density structure, whereas your paper actually implies this objective. The next report, signed by candidate of Geographical Sciences, head of Laboratory of St. Petersburg Department of the Oceanology Research Center, Madam Tikhonova. The report is in favor of the defendant. The following critical remarks are said. It would be better to include a contemporary understanding of the pumping. In the fourth chapter, it would be reasonable to compare the calculations with laboratory research. Chapter 5 would benefit from looking at the impact of temperature on water density. The next report, signed by Doctor of Physical and Math Sciences, Head Research Fellow of Oceanology Department of Roshydromed Research Center, Mr. Timokhov. The report is in favor of the defendant. The following criticism is said. In the first chapter shows that in the density lenses, the gradient according to hydrostatic and non-hydrostatic models are similar. It would be also exciting to look at cases when the density lens is on the surface of the sea, what we can see in colder weather spans. In that case, the horizontal pressure gradient in the lens region calculated by hydrostatic model would be equal to 0, whereas in case of non-hydrostatic effects, the horizontal pressure gradient would be different from 0. Next point. In density simulation, the water density everywhere is over the initial sea density. However, this is a valid term only in winter, whereas in summer, due to temperature rises, due to upwelling, the density will be lower than the average density, and then the water can downwell only to the horizon of its density. And lastly, it would be adequate to have the calculation of density for the regions such as Barmhole Basin of the Baltic Sea, where we have some data in massive inflow time spans. It would be valid to relate this to density, salinity fluctuations, and to compare those with your simulation results. Next report, signed by member of the Dissertation Board, Doctor of Physics and Maths Sciences, Professor of Oceanology Department of St. Petersburg State University, Mr. Roshkov. The report is positive. The following criticism is said. The text of the paper has not accurate. Well, it is understandable, but anyway, always you have to make guesses because some words are missing and there are lots of misprints. Next, the role of laboratory simulation is not clear. In Chapter 2, the term disturbance is used without any explanation, stochasticity or non-linearity. Both series of stochastic differential equations and determined equations are very well developed. However, instead, the author refers to a third approach where you have to substitute the term disturbance. Fourth, this model does not take into account the interaction between temperature and density, whereas temperature can indeed dominate or impact density structures. Fifth, when modeling the water spread within the Barents Sea, the initial understanding was that density is homogeneous, whereas in reality what we see is a fluctuation of density. Moreover, the density depends on the depth, and this has to influence the density distribution as well. Next report, signed by member of the Dissertation Board, Doctor of Physical and Mathematical Sciences, the leading research fellow of the Antarctic and Antarctic Research Fellow, Roshydromed, Mr. Ivanov. The report is in favor of the defendant. The following criticism is expressed. First, there are some stylistic inadequacies. For example, there are repetitions of words, and sometimes sentences are not adequately structured. Page 6, quote unquote, the results of such research can validate our understanding of the mechanisms behind the salinity variation, heat variation, oxygenation, and chemical elements concentrations. Oxygen is a chemical agent, so why is it repeated in this same phrase? A number of illustration is done in black and white. For example, illustration 4.4, 4.6, and some others. 4. The concept of the term pumping has not very well been validated in domestic literature. For example, on page 76, it would be beneficial to have some definition of what pumping is. The next report, submitted by member of the Dissertation Board, Doctor of Geographical Sciences, Professor of Oceanology Department, St. Petersburg State University, Tatiana Belonenko. The report has the following critical points. On page 22, the defendant says, when validating the hydrostatic approximation, we proceed from the fact that density fluctuation occurs along with isobars, which means it is horizontal. I can hardly agree with that, and therefore we need an experiment, a numerical experiment, to model this particular setting. Moreover, it would be valid to assess the implementability of this model depending on the environment. Second, Chapter 5 develops a model to implement this simulation in the White Sea aquifer. However, there are only scales. The illustration 5.8 is not clear because there is no scalability. So this inadequate and non-transparent result is compared to the data obtained on the field. And then, based on that, the key conclusion is made on the implementability of this model. Third, the way the dissertation is drafted is actually inadequate. Sometimes phrasing is disrupted, and there are some abbreviations that are not clear. The next report is signed by a member of the Dissertation Board, a Doctor of Physical and Mathematical Sciences, the Senior Research Fellow of Polar and Sea Research by Alfred Wegener, Mr. Androsov. Alexei Androsov, the report is positive.
And the following comments were made. One of the important components of modeling the process of distribution of near bottom density water is the parameterization of friction at the bottom. The author used the Ackerball ratio to parameterize the tangential friction stress at the bottom. This parameterization was obtained by Ackerbohm in 1908 and was used by him to parameterize the friction between the lower boundary of the atmosphere and the Earth's surface. How well is the application of this parameterization for the distribution of density waters is missing in the thesis. The problem of turbulent closure, second, is an equally important component of modeling vertical process in the ocean. There is no mention of a numerical model for obtaining the coefficient of turbulent viscosity. But without a turbulent closure, the system of solved equations is not closed. 3. The choice of the coefficient of horizontal diffusion also remains outside the scope of the work. If this coefficient was chosen as a constant, then it was necessary to justify this choice. 4. The choice of the numerical scheme used in the work is widely used in the modeling of coastal process in order to simplify the implementation of the drying and flooding schemes. Due to the lack of these processes in the model, the choice of the numerical scheme raised a number of questions and the connection with its more complex implementation in comparison with the one-step scheme. The numerical realization of the scheme requires additional accuracy. Coordination of three-dimensional and two-dimensional problems is another thing. Such an agreement reduces not only to the calculation of additional equations for the velocity pulsation and their allowance for the velocity averaged over the vertical, but also to the flexible parameterization of bottom friction in the averaged equations of motion. In this formulation, the use of vertical averaged velocities for the parameterization to the bottom friction is not permissible. The most difficult moment is the allowance for transport velocities in the trace equation, which for centering the circuit should be selected in the middle of the step along the time of the baroclinic problem. And fifth, setting the condition on the open border when calculating the test experiment and calculating the density flux in the wide sea requires some explanation. The above condition, page 87, reflects the relationship between velocity, averaged over the vertical, and the level. Such a boundary condition can be implied only for the average problem, averaged over the vertical, provided that one of the variables and the sufficiently slightly verifying bottom relief are known. What are the real boundary conditions for the three-dimensional problem? 6. What does the author mean by using a special curvilinear system for describing the near-bottom density flow in Chapter 3? And why the numerical scheme is given for a different virtual coordinate? And different from the statement of the problem. 7. The author of the work in modeling the density flux of the wide sea speaks of the lack of information on the way of distribution of bottom water and its interaction with the environment. In fact, this is not so. In recent years, there has been a sufficient number of works on the study of this project, both in foreign literature and in Russian literature. I will only mention a few works: Ozil and al. 2016 in Ocean Science 12, and Atham et al. 2012, J. Climate 25, and so on. Bashmachnikov et al. 205, White Sea Hydrodynamics and Marine Ecosystems, Springer. And also the last this comment is from Professor Doctor of Geographical Sciences Zakharchuk Evgeny Alexandrovich. The following comments are made, the following critiques are made, and Podrezova Nadezhda considers the influence of the Barents Sea waters as the main factor influencing the formation of the oceanological regime of the White Sea, and she ignores other no less important factors. Number two, in our opinion, the justification of the use of the hydrostatic approximation of by the defendant in the density flux model doesn't look convincing enough against the background of the result of field studies of the cascading phenomenon described in the works of Drs. Ivanov. It is not clear why, for more convincing proof of the use of the hydrostatic approach, the applicant didn't compare the results of two numerical experiments, one of which would use a hydrostatic model and the other would use a non-hydrostatic. And number three, the lack of a justification for using the linear approximation in the equations of motion and bottom friction. Non-linear effects associated with the bottom friction and the influence of advective accelerations can have a significant effect on the dynamics and structure of density flows in the bottom layer. In this connection, it is not clear how the linear approximation and the interactions between baroclinic and barotropic components of thermodynamic process can be realized, which is ascertained by the applicant on page 47 in section 3.4.3. And it is also impossible to agree fully with the conclusion presented by the applicant in paragraph 3.4, according to which the mathematical model presented in paragraph 3.3 describes only barotropic and baroclinic long gravitational waves. For a more correct, number 4, for a more correct statement of the numerical experiment, the average long-term salinity field in the White Sea should be used as the initial conditions. Well, I've read out all the comments from our esteemed reviewers. I would like now ask the defendant to answer these questions, please, and comments. Yes, please. I would like to start with Valentin. I answered about the laboratory modeling and simulation. As far as the perturbation, the term perturbation is used in terms of deviation from the non-perturbed, non-moved state, and the terms of the temperature. I agree with the comment, and I would like to include the temperature into my calculations. As far as the comments from outside org, I agree with Dr. Tikhanova's comments. As far as the lens that is above the surface, it's a very interesting case, and we're going to focus on it. As far as the spread of fluxes, intensity fluxes in the sea, the intermediary layer is a more complex problem, and we're going to study it in the future. We have to have a different grid, and as far as in my work, the grid is perturbed at the bottom, but we have to study a central perturbation there. And the third, we can use this model not only to the inapplicable to the White Sea, but to the Baltic Sea as well. And Vladimir's critique, I agree with all your comments. Dr. Reshka. Belanenko Tatiana Vasilyevna. First, just the possibility of using heteroception. In fact, the density flow prevails predominantly, and this is supported by theoretical observation, theoretical experiment, observational data, laboratory research. Mr. Zakharchuk, the first one, the Barents Sea case study, the White Sea case study. The example of the White Sea, the possible consequence of formation hydrological characteristics, it was not part of the to study that was not part of the paper. The second one, the main factor forming the motion of density flow is in the inclined bottom is the horizontal pressure gradient. Therefore, the difference of the results of the application of the hydrostatic modes determined by the difference of the description with the help of the horizontal pressure gradient in the region of the bottom density flux. The third comment, the factor of the predominant motion of the near bottom density flow indicates that the dynamics of this motion is determined by geostrophy, and the contribution to the remaining components, including nonlinear ones, is of secondary importance. The vertical currents that form in the region of density flows under the influence of bottom pumping cause sea level disturbances, which leads to the formation of barotropic horizontal currents. Barotropic currents participate in the advection of salt and thus in the propagation of density flux, which is a baroclinic process. This is their interaction between baroclinic and barotropic process. The next one is about mathematical models. I agree. The model includes barotropic and baroclinic process. I should have said in the paper. As far as the temperature, I also agree. And in our further research, I'm going to add that. And Mr. Drosov, Alexei Anatolievich, the first one, the ratio that was is true if the structure of the currents in the bottom is which are formed under the influence of constant horizontal pressure gradient. I used the regions where this condition is true. I used the ratio of the Eichelblum in two blocks, in the block of calculating the barotropic adaptation process and in the block for calculating the vertical velocities of the currents formed under the influence of bottom pumping. And this Eichelblum coefficient ratio has been used, and it still holds. The second one, in the model, the distribution of the coefficient of vertical turbulent viscosity was specified, and for simplicity, the consideration the process of formation of turbulence in the region of strongly stratified near bottom density was beyond the scope of my paper. In the White Sea, the generation of turbulence of the bottom layer, the tides have a significant effect. Therefore, when including the turbulence coefficients, it would have been also very good to include a description of the tides. The third one, horizontal turbulent diffusion, the process under consideration plays a secondary role in comparison with advection. Therefore, I didn't really focus on that. The fourth one, Baryklian three-dimensional distribution problem near the bottom, and barotropic two-dimensional problems are considered separately because they simplify the problem of the structure of the influence of pumping on the vertical velocities. The fifth one and the third, there were no derivatives on the vertical. I agree with the sixth one, the curvature. I mean that the vertical coordinate was not z, but with a value sigma that has to do with the thickness of the region. And the seventh comment, as far as the source, I saw all these sources and I read them. In the first one, there was no White Sea, only Barents Sea, and in the other ones, yes, the more simulation of the White Sea, but the vertical steps were too large, and the bottom layer was not touched, and there was no pumping, and they didn't investigate, and they don't have anticyclonic circulation, and they admit that, and the authors connect the circulation of the in the White Sea with the isotopes, and so we have. They don't have the picture that we have in my paper. As far as the monograph and the C's of the USSR monographs, it also doesn't focus on the 10-meter bottom layer, and I agree with the comments about typos and other inadequacies. Yes, totally agree. Thank you very much, Nadezhda.
Distinguished colleagues, do you have any questions to Nadezhda? Well, can I ask my question? Well, as for your reply to the horizontal diffusion that dominates, but you actually use a linear pattern, and therefore you cannot say that it dominates the advection. Well, I actually did not say that it is insignificant. I say that it is not significant. It is not as dominant as the horizontal advection. Yes, indeed, but you do not look into horizontal advection in your system. So in equations, do you have advection members? Advection values? No, I don't. So did you include the horizontal advection? Yes, I did. Well, how come? Well, you have a linear system. What you write here is that you do not include the motion equation. So you have only in specific advections, you have the horizontal advection. Those are not linear equations, actually. Well, what we have is that you do not include horizontal advection in the linear equations. Well, on the first slide, I do not see the horizontal advection. This is the equation of salinity variation. I mean the horizontal diffusion in motion equations. You have two constant values and two transient values. And all that at the same time you say that it is not as important as the horizontal advection, but you do not include the horizontal advection in your motion equations. I'm not speaking about the salinity equation. I'm speaking about the momentum equation. No, I do not include the horizontal advection in the motion equation. Well, then it is not clear how come that the horizontal advection has little importance. But because actually it is vice versa. The advection dominates the diffusion, but you do not include the advection. How can you explain this discordancy? Is the question clear to you? No, it's not clear. You do not include horizontal advection in motion equations, but you give an answer to the horizontal diffusion, and you say that the horizontal diffusion is less dominant than advection. Not the advection values, but the advection overall, but you do not include the advection values. In your mind, those dominate the horizontal diffusion, have a more significant impact. Okay, I will include that in the future. Thank you. Thank you. More questions? Are you satisfied with responses? No questions. All satisfied. Thank you very much, Nadezhda. Please do wait. Maybe members of the audience have questions. No questions from members of the audience. Then, Madam Podrezova, thank you so much. And now we follow the agenda. And we'll give the floor to the research supervisor of Madam Podrezova, Valery Tsarov. Professor Tsarov, the floor is yours. Well, the defendant Podrezova was admitted to the postgraduate department after she did her master's degree. Her first scientific supervisor was Mr. Doronin, but somehow, after she took a maternity leave, she was, in 3 years after, back to the postgraduate department, and regrettably, Mr. Podrezov expired by that time, so I was compelled to be her research supervisor. Initially, defendant Podrezova looked into 3D simulation, something like Preston modeling, and she looked at dynamic processes and the calculations she used to show that seasonal processes, I mean salinity fluctuations, temperature fluctuations, work very well for these calculations. Whereas in continuous calculations, what we saw is that the density was going down. So, and therefore she came to an idea that this may influence the bottom densities fluctuation. Therefore, she decided to look into that field, and this is how this paper emerged, actually. While working on this dissertation, I believe that defendant Podrezova is a creative and very well qualified and trustworthy researcher. She is now a senior lecturer. She lectures general oceanology. She participates in such seminars as the physics of the ocean, information systems, researching oceans. She supervises some on-field works bachelor papers. And her students actually were top on the international student competition. Therefore, I urge you to vote in favor of this paper. Thank you, Valery Anatolievich. According to the agenda, we are going to have a 5-minute break to discuss the results of the defense and to decide whether Madam Podrezova has passed or failed. So please switch off the audio devices, switch off the broadcasting. I urge everyone all members of the audience, except for members of the dissertation board, to leave the room.
Я вас не слышу. Сейчас очень плохо слышу. Я слышу, что вы...
Алексей, сейчас,
вот,
сейчас слышно?
Да, вот сейчас хорошо, сейчас слышно.
Так, коллеги, ну, какие будут наши выводы относительно защиты? Надежда Алексеевна.
По очереди мы просто говорим, да? Да. Ну, значит, я могу сказать, свое мнение. Собственно, я с работой знаком достаточно хорошо, потому что еще примерно год назад предполагалось, что это будет защита в другом формате, в гидрометинституте, и меня просили быть оппонентом. И честно скажу, что вот первый раз, когда я работу прочитал, там было немножко другое название. Это, собственно говоря, оно называлось «Модель». И мое основное замечание и предложение по модификации было в том, что сейчас уже не то время, когда можно реально предложить какую-то сверхновую модель, которая будет лучше, чем то, что существует по большому счету. И было предложение больше переключиться на результат применения модели к процессам, в частности, в Белом море. И это предложение было, собственно, услышано, и немножко была перефокусирована работа, и, на мой взгляд, она стала более интересной и более актуальной в каком-то смысле. Мое впечатление, что в целом соискатель показал, в общем, достаточно высокий уровень квалификации, создав, в общем-то, инструмент. Там можно, дебатировать, насколько он будет, полезен его там дальше продвигать, или все-таки, пользоваться какими-то продуктами, которые вообще сейчас есть на рынке, как NIMA, например, какой-нибудь там MIT JCM, который, с моей точки зрения, в зависимости от их настройки, они, по всей видимости, все-таки эти процессы воспроизвести смогут. И, преимущество того подхода, который мы сегодня услышали, в том, что автор явно, расчленил эти отдельные, компоненты бароклинную, баротропную, показал их вклад, что, наверное, можно и в большой модели сделать, но это тоже требует усилий, другого сорта просто. И в этом смысле результат, мне кажется, вполне позитивный, как работы, которая, в принципе, заслуживает той квалификации, на которую она выдвигается. Вот такое мое мнение. Спасибо.
У меня есть мнение. У нас на всех в интеграле 5 минут, поэтому я скажу кратко. Мне работа понравилась, чувствуется школа Юрия Петровича Доронина, школа Гидрометинститута. Я буду голосовать за.
Спасибо.
Я голосую за.
Я тоже свое мнение в отзыве высказал, что это начальный этап развития работы, и, в принципе, я тоже голосую за.
Спасибо, Алексей Анатольевич. Я считаю также, что несмотря на недостатки, работа интересная, актуальная, я тоже буду голосовать за.
Dear ladies and gentlemen, dear members of the Dissertation Council, dear guests and colleagues, our session is continuing. I would like to switch on the broadcast and make sure that it's working. Is the broadcast working? I'm tabling the motion if for open vote to award the degree. As you know that if more than half of the Dissertation Council membership, but not less than two members, the positive verdict is reached, and this is according to the to the bylaws of St. Petersburg State University. So the motion is the resolution. Who is voting in favor of awarding the candidate of physical and mathematical sciences 20 in the field 2500, 20 oceanology? Please vote. Yes, no nays, no abstentions, and that means that I declare that 5 out of 5 members of the Dissertation Council voted in favor of awarding Nadezhda Podrezova the degree of Physical and Mathematical Sciences, PhD in the field 25.00.28 oceanology. The verdict is positive, and it's reached. And now I would like to give the floor for a final word to the defendant. Please, Nadezhda. I would like to express my gratitude to my research supervisor, Professor Valery Tsarov, for this work and for proposing to me to do this work and for guiding me through so many hardships and you know how many tears were shed and how much hardship I had to go through. A lot of my gratitude to Vladimir Vladimirovich. You were the first to read my paper, and thank you for your criticism, for your recommendations. And thanks to you, the dissertation has the shape that it has now. Great thanks to Professor Androsov for joining the Dissertation Council, and also Tatiana Vasilyevna of the Department of Sociology, and Evgeny Alexandrovich for accepting my paper, my thesis, for your recommendations, and your kind attitude to my work, and thank you a lot. Thanks to the Expertise Center for your great attitude, and I know other examples. I know I have experience, And I would like to close this session. Thank you very much for your participation.